Yeah, my name is Nebel. Me and Ansgar, we work as PhD students at the TU Dresden in the group of Oliver Sonder, who does numerics of partial differential equations.
So yeah, I'm Ansgar Burchardt. Yeah, as Lisa said, I work in the group of Oliver Sonder. Yeah, I was here a bit longer in the group, and we had already been using containers for some purposes like CI systems. And so I had the idea to use the same also for my computations on the local cluster, so Taurus. And I also recommended to Lisa to do the same. And yeah, she will explain our motivation a bit and her problem.
All right, thank you. So yeah, today I will talk to you about our use case for using containers on our high-performance computing cluster at TU Dresden, that's Taurus, and we do finite element simulations with the DUNE framework in C++. So the project that these simulations cover, we do the simulations for experiments with a bilayer system. That is a project of the Institute for Numerical Mathematics at the TU Dresden here, and of the Leibniz Institute for Polymer Research in Dresden. And the goal of the simulations and the experiments is to create wrinkles of a specific wavelength and control the splitting behavior when we have wrinkles of one wavelength transforming into wrinkles of another wavelength. And here on the bottom of the slide, you can see the experimental setup. So we start with elastic polymer layer, and we stretch that, and then different specific areas get different gas treatments, and this creates different material properties depending on the gas treatments that the areas receive. So here you can see at the polymer layer on the very left, and there's a mask that's covering part of that, and then we have first a treatment with the mask, and we remove the mask, and then a second treatment. And then we have different areas with different material properties. And afterwards, we let the elastic polymer layer relax again. The whole layer shrinks, and then we have wrinkles forming, and the wavelength depends on the treatment this area has received before. And what's specifically interesting to the people from the Polymer Research Institute is exactly the boundary of two different areas. So where wrinkles of a big wavelength merge into wrinkles of a smaller wavelength. And they would like to have simulations that kind of repeat the experiments in a numerical way. So this is what we were doing as a simulation. And to do that, we combined a model from three-dimensional elasticity and a two-dimensional Kossara model. You can see that on the left here. So we have the polymer layer, which is three-dimensional in blue, and on top, in 2 dimensions, you have a thin shell attached to the polymer layer, and then you can see the wrinkles that form in the shell in the attached shell. From these models, we can derive a mathematical minimization problem, and we are looking for a deformation function that realizes these wrinkles, and we look for the deformation function in the set of all admissible deformation functions. So from the combination of these two models, we can construct an energy function that represents the energy of the whole system. This energy function is possibly, or very likely, nonlinear and non-convex. And we would like to find a local minimum of that. And then we know this minimum is the deformation function we're looking for. Here on the right, you can already see some of the results. So you can see where the gray is the simulation that we did, and the yellow one is the actual experiment. You can see that this is like the scales here are micrometers, so it's pretty small and pretty tiny. And we are interested exactly in this in these fine structures where the big waves, the big wrinkles merge into the smaller wrinkles. Okay. So now we have this nonlinear and non-convex minimization problem where we want to find a local minimum. And unfortunately, as the problem is nonlinear and non-convex, we can't solve that in one step, but we have to solve that iteratively. And we do that using a trust region algorithm. That is an algorithm that is similar to the Newton's method. Newton's method, probably some of you know, is used to find the root of a function. The trust region algorithm is used to find a local minimum of a function where you can't directly see where it is. So what we essentially do is we solve it iteratively. So we start with an iterate, and then at the current iterate where we are, we do a quadratic approximation of the function and try to minimize this quadratic approximation instead. So in the picture here, you can see the function, which is kind of W-shaped, and then the current iterate, which is in the middle of the blue region, here denoted by xk, and then a quadratic approximation at the point xk. And now we want to minimize this quadratic approximation, but not everywhere in the whole domain, because the quadratic approximation is not a perfect fit for the whole function. It's just a good fit close to the current iterate. And this is why we minimize this quadratic approximation inside the so-called trust region. So this is the whole blue area here. Yeah, and at the end, when we have minimized this quadratic approximation, we get a correction that we can add to the current iterate and then move on iteratively until we find a local minimum. Okay. So this problem, to solve this problem in a simulation, comes with a high effort because, as I said, we have this nonlinear non-convex minimization problem. So we need an iterative solver, which of course increases the effort a lot. And in each iteration, we have to do two things that are kind of expensive. We have to do the quadratic approximation. So we have to calculate the first and the second derivative of the function at the current iterate. So we have to assemble the values in the matrix vector system that we achieve afterwards. And we have to do that for every iteration again, freshly, because we always update the current iterate, so these values change. That is quite expensive. And also, in each iteration, we obtain a quadratic obstacle problem, which is also hard to solve. Also, we need to use finite element functions of second order, because otherwise we would get locking effects. And locking effects, I don't know if you know what locking effects mean, but it essentially means if you use the wrong finite element functions, then the simulation does not look like the reality anymore. And this is what we want. We want to reproduce the experiments that were done in reality at the Institute for Polymer Research. So yeah. This finite element functions of second order produce have the effect of a high coupling of the finite element functions, which make the quadratic obstacle problem even more expensive to solve. And also, we're interested in fine structures. So we need to use a fine grid exactly where the shell is attached. And this makes the whole system large, which, yeah, resides in a high effort. So we implemented the simulation in DUNE. you can see the webpage here. And also, I will share the slides afterwards, so you will find the links here. DUNE is a toolbox for solving partial differential equations in C++. It is free software licensed under the GNU General Public License. And here on the right side, you can see a book that was published by the end of last year, written by our professor. And yeah, it's on the published by Springer. And if you're interested, then you can just click on the book, and then you will be redirected to the Springer website, and can have a look. Yeah. So the DUNE software is structured in modules. And there are different kinds of modules depending on what simulation you want to realize. There are core modules that give you like a grid manager and some options to evaluate functions on the grid. Then you have discretization modules that give you kind of a structure for finite elements, and then an application layer that is here in orange on top. And my simulation would belong to the application layer that uses a lot of DUNE modules that are beneath it. So already, like within the DUNE framework, I have some dependencies and some software blocks that I use and combine. So as I said, to use DUNE, and we implemented the first region solver that I just explained to you. And to repeat once more, like in each iteration, we have to do the setup of this quadratic obstacle problem, and then solving the quadratic obstacle problem. And both steps take a long time. The first one, the assembly of the first and second derivative of the function, is done with an automatic differentiation program called RLC. Maybe you know that, like one of the most famous ones. And this step is parallelized with MPI. So we have the grid distributed on different processes, and then each process evaluates the first and the second derivatives exactly at the points that this process is responsible for, and then fills in the structure into the and then fills in the values into the vector matrix structure that we obtain afterwards. And as a second step, we need to solve the quadratic obstacle problems. This is done using a multigrid method, which is again iterative. So we have an iterative solver inside an iterative solver. And this step is not parallelized yet. So this runs on one process only. So the problem is set up, and then the whole problem is gathered in one process, solved, and then the solution is distributed again to all the different processes. So for the next iteration, you can evaluate the first and the second derivative again, and so on. Okay. So these simulations, they got pretty, expensive. And this is why at some point we chose to run them on a high computing cluster. At Dresden on Taurus. And another question was how to move the simulations that so far were running on my local machine to Taurus. And we essentially had two options to do that. The first option was to run the simulation directly on Taurus with the module system there. However, we didn't like this idea because that would have meant breaking the whole setup. And also, I was still doing local development, and to make sure everything runs locally and on Taurus, I would have to, in the end, bring the setup of Taurus to my local machine, so work with a module system locally as well. And another problem is that I have many dependencies that are not all included in the module system. So I need this automatic differentiator to calculate the derivatives. I need something to partition the grid, and then I need linear algebra packages that DUNE depends on. not all of that is directly available there. So the second option, running the simulation inside a container, being much more attractive, because that means we bring the local setup to Taurus, which means the ongoing local development is easy, and all dependencies that I need are in Debian. I have a Debian-based system locally, and if I use a Debian-based container, then I can just add any dependencies that I need to the container definition, and don't need to worry about that anymore. Another good thing that comes with the container use is I have the option to build the simulation inside the container and then give the container to others. Yeah, actually the Institute for Polymer Research, they were specifically at some point asking for the container so they could do the simulations themselves and play around with some parameters. So then it was very easy to just give them the pre-packaged container, and yeah, they were really happy about that. So how does my current workflow now looks like this? I built the container locally, push it to a repository. So I use Docker, and as Azad already said in his presentation, that's probably that's what most people use. Yeah, then I load the container on Taurus using Singularity, which is also what most people use. If I have not built the simulation yet, I built that inside the container, and then start simulation inside the container using a batch file. There are some difficulties that I encountered with that, so maybe that is now useful for you because you are admins and probably you also do with documentation how to do that. So when loading the container in Taurus in Singularity, that was somehow straightforward, but the Singularity needed like a temp directory, and I had to change that to a temp directory I could access because it was as a standard set to /temp. And I could not really find documentation about that, so this is something that we found out by ourselves. Yeah, and then everything else works fine, but we actually have problems with the MPI support when trying to run the simulation on several nodes. So this is going to be like the hardest, the hardest problem that we have encountered so far, and it's not completely solved yet. So what works fine as of now is starting the program inside the Docker container on one node. So here you can see an excerpt of the batch file that I used. So I start the container and then do a call to MPI and then start the simulation with a parameter set. And I use the maximum number of nodes, the maximum number of tasks for one node for MPI. And this works fine. So I could do a lot of simulations with this technique. And the problem with this is that I already used the maximum number of tasks for MPI, but actually I would like to start my simulation on more nodes, not just one. So the thing is, it's not essentially clear how to do this, that the Open MPI installation inside the container is able to use the InfiniBand hardware on Taurus and kind of communicate across different nodes. So this is kind of one attempt on how to do this. So we actually told MPI by setting allow InfiniBand to true to use InfiniBand ports for communication. And then we also told Slurm to use the PMix API to do the communication, and this long excerpt of the batch file starts, and distributes the grid as intended, but unfortunately we still get a communication error during the setup of the problem and the calculations. So there's still something going wrong with the communication across different nodes. But yeah, this is one attempt I did with 69 processes, and here you can see kind of the distributed grid. Yeah, but this is something where I would need more documentation and more help, because maybe there's still something wrong with how I call the simulation inside the computer. That is not completely clear yet. Yeah, so far for my workflow and how I use containers and Taurus. Now I will actually show you some results of the bilayer system that I showed you in the beginning. So what I did is that we have this 3D elasticity block with a shell on top. So I already refined the grid exactly where the wrinkles are supposed to form. And this whole system now has 477,000 degrees of freedom. And to solve that, I need 61 of these iterative plus region steps. And here I already parallelized the step where I set up the problems on 27 tasks on one node. But and this is already like a huge improvement, because now it takes like 6 minutes per step to set up 6 minutes for one step to set up the problem and 10 minutes to solve it. So a total of 16 minutes per step. And if I would have to do that, yeah, not parallel or even on my local machine, then it would take much longer. Yeah, but of course, finally, this is not what we want, not what we want in the end. This is okay for now, but actually we would like to have this with a much finer grid. So this is an example that I calculated that has 2,660,000 degrees of freedom. And here you can already see it takes a lot longer. But actually, if I could do that, I would like to do that, like even with yeah, a bigger grid and with a finer grid. So that would be the ultimate goal. Yeah. And then on the last slide, you can see the simulation of the tri-layer system. This does not include only one shell on top of the 3D polymer layer, but another one. And this was an experiment that another researcher at the Institute for Polymer Research was asking us for, because yeah, we were already able to reproduce this like splitting up of the wrinkles. They were interested in more simulations from our side. And for this one, it has 389,000 degrees of freedom, and yeah, takes around 11.5 minutes per step. So, yeah. So this is my last slide. So I will go back to the slide with the workflow. If you have any questions, then now Ansgar and I are here for you to ask us anything you would like to know.
Yeah, I have a question. You said that you use Singularity on Taurus, and why you decided to use Docker images? Because the source software was provided as Docker, or because it was easier to deploy on your local machine or something else?
So it's easy to deploy on the local machine, and we already use Docker in the CI system with GitLab CI, and so it's already somewhat familiar for us, and we don't have to learn yet another system.
Thank you very much. Thank you very much. Then, if there is no other question, we can go forward with the next presentation. We just have time to prepare it, probably, so we'll not lose time on preparation. But if you have any questions left, then please ask now. We still have time. So, if not,
question, Asad, if you would allow,
yes,
regarding the temporary directory that caused some issues with Singularity. So wasn't it the fact that you had no access to /tmp, which is kind of strange because I think on most clusters users have access to /tmp on the nodes, or that you needed the output that was written to /tmp is saved on a permanent place?
I know it's something. So Singularity uses it for converting the container, I think, and I think some security policy did not allow using the globally accessible /tmp. So I don't know which security module was it, but I didn't like using it, so we just used a different directory. Here in the chat, Danny Roger says, for security purposes, we restrict access to /tmp on login nodes. So that was probably the issue. But of course, if you then just use Singularity for checking if everything is there, then we just get the error and are a bit confused for a moment.
Okay, thanks.
Yes, but then this would be something like useful to add to the documentation. But yeah, of course, you're not supposed to do stuff on the login nodes. Yeah, that's true. Yes, but everything that you can, like all the problems that we have encountered so far, if somebody else encounters them, then they can already read the answer and yeah, don't have to look for that themselves.
And I think we have a question from Samuel.
Yes.
Probably a short question.
A short one. How did you choose the base container? Did you choose it like something Ubuntu or Debian, or maybe there are other containers around, for instance, from Intel or from NVIDIA or from AMD, which are maybe adapted for the hardware with optimizations?
No, we just used the standard Debian containers because we also wanted to use the software already built for Debian, like FLC and other libraries, sweet sparse, so we don't have to build it ourselves. And well, we were already using Debian locally, so that was the main reason. Of course, you can use some other base containers that might run a bit faster, but I think that's a later optimization.
Okay, thanks.
Yeah, for now, the main goal was to keep the kind of the step from the local development to Taurus easy, and like the first optimization thing that we have to fix is the MPI support in several nodes, then parallelize the second step of the whole iteration. So now we have only the first one parallelized, so we set up the problem, and the solver is not parallelized. And then, yeah, then for the fine tuning, that would be something to do then.
Thanks.
Thank you very much once again.